Welcome to Chemistry 111. But you're finding things well. Today is the last day of the 9-week grading period, so I'll be updating the grade books and all the relevant stuff. The last day to drop classes is coming up, so if for whatever reason you don't think you're going to make it, may come talk to me first. We can look at your grades together, but the last day is coming up. Let's see. What is it? Last. I swear I didn't delete it, but it's coming up really, really soon. Oh, I'll be keeping that in mind. Last day to drop is 3/29. Now, I've sent out a survey about the test 3. Where the idea is that it will be done in person, on campus, ideally sometime around 7 p.m. Now, not everyone can make it. I did a survey on what day the most people can make it. So please reply to that if you want to have any sort of control, any chance of figuring out a day where you can make it at the same time. However, if you cannot make it at the time that I select, meet with me, figure it out. Do it during a lab period. Sometime during the day. I'm usually here from 9 till 1 on most days, and from 1 to 3 on the Tuesday through Thursday day period. So come find me during a free hour or two during one of those times, and you can take that test. I want to get it all done this coming week. It's going to be 20 questions, mostly multiple choice. There's a couple drawing ones, but there's mostly multiple choice. And so I'm going to show you what that's going to entail. So to start things off, we're going to look at the homework for Chapter 8 and then look at last year's test for these last 3 chapters. As this year's test is going to be rather similar types of problems. So, okay, we'll go ahead and get started. Homework. So I'm going to go ahead and skip balancing. Hopefully you can balance these guys without much problems. So not going to worry about those. Recognizing reactions, be able to do this. You have single replacement, combination. They can either be called single replacement or single displacement. Either one, good, but that's one element exchange, a cation or anion exchanges with another anion. It goes from element to compound and compound to element. Combination is 2 things come together to form one thing. Decomposition is 1 thing breaks apart into 2 things. Double replacement, cation and anion pairs swap places. So this one is one compound breaks apart into 2. So that's a decomposition. This we have 2 compounds come together to form 1. Now, this guy is also a redox reaction, oxidation reduction. An easy way to tell is that we form a pure element. This one is not, however. If you check, calcium is 2+, oxygen is 2-. Carbon is 4+, oxygen is 2-. Calcium in this case is still 2, carbon is still 4, and each of the oxygens are still -2. So this one is not a redox. In this case, we have sodium nitrite and hydrochloric acid swap places to form sodium chloride and hydrogen nitrite or nitrous acid. So this is an example of double replacement. Na and the H swap places. This one's zinc sulfate and magnesium solid goes to zinc solid and magnesium sulfate. That's a single replacement, and that's also oxidation reduction. Easy way to tell is pure element, pure element. Whenever you have a pure element, you're almost always guaranteed a redox reaction. Say acid-base neutralization is when acid plus base form water in a salt. Precipitation is when two aqueous solutions form a solid. Redox is when oxidation state changes. And none of the above, it doesn't fit any of these above examples. This one, barium perchlorate, we just did that one. That was a redox. Sodium chloride and potassium sulfate, they're both these aqueous. Switch to sodium sulfide, potassium chloride. This is not acid-base because they're neither acid nor base. It's not precipitation because there's no solid being formed. If you check the charges, there's no oxidation state changes, so it's not a redox, so this one's just none of the above. This case again, we said carbon is 4, calcium is 2, oxygen is -2, that's also none of the above. And this one, hydroxide, potassium hydroxide and silver nitrate forms potassium nitrate and silver hydroxide solid. So aqueous forms a solid. There we go. What? Oh, there's one more. Good Lord. Okay. Barium hydroxide, it's a base. Nitric acid is nitrous acid is acid mixed together to form barium nitrate and water, liquid. So that's just an acid-base neutralization. So, okay. Strong electrolyte, weak electrolyte, that's not going to be as big of an issue, but large organic stuff is typically non-electrolytes. Strong acids, strong bases are strong electrolytes and soluble salts. Weak acids like ammonia and vinegar, which is acetic acid, are weak electrolytes. So, but rather than just trying to guess that, there is actually a conductivity interactive. You click on that, it brings up like a beaker, which you can fill with these imaginary liquids and then put a light bulb to it. And depending on whether these are electrolytes or not, or the strength, the light bulb will either light up strongly, light up weakly, or light up not at all. And that way you can test whether these are electrolytes. So it serves better to actually test those. Acid bases or salts. Okay, and this is not a big issue about the acid base thing. They go ahead and try this problem, but it's not super crucial. Let's see. Go back and actually hit some of the important ones. Okay. Oh, shoot. All right. You're going to skip just the important ones. Okay. So strong acid, weak acid. Basically, strong acids, any halogen acid except for HF, nitric acid, and sulfuric acid are your only strong ones. Any other acid is typically weak. Though I'm pretty sure the hint here, like there's a link to strong acids that you might need to memorize, but those guys are all strong electrolytes. Less likely to be an issue. Okay, let's look at a real problem. Just practicing here. Okay. Now, just splitting this apart. This is good practice for, say, when we do the net ionic equation. So when cadmium chloride breaks apart, you need to be able to recognize that chloride is typically 1 minus. And there's 2 of them, so cadmium would by definition have to be 2 plus. So we'd put cadmium 2 plus, down, hit the aqueous, and then because there's 2 chlorides, it's not Cl2, it would go to 2Cl 1 minus. So just make sure you understand when you're breaking them apart. I've seen too many people break apart cadmium and chloride, and they have a Cl2 2 minus. That's not how these things break apart. It's basically, we write them adjacent to each other to make it clear, but really it's Cl, Cd, Cl. It's they're the surrounding cadmium, like 2 bouncers removing a drunk from a bar on either side to help guide him out. Okay, so this one, complete the solubility table. Okay, this one, you can actually view them and actually mix these guys together and see what's going to happen. And then you just, bada boom, bada bing, pick soluble or insoluble. However, there is a chart you will have to be able to use. In this particular problem, they say use the interactive. But in some cases, there's a chart. So this particular problem, you will use a chart and you'll cross-reference. If I put this cation and this anion together, what's going to happen? And so, for example, lead is usually insoluble except when mixed with nitrate. Barium is usually soluble, but I don't think it's soluble with sulfate. Carbonate is usually insoluble. And then but sulfate is soluble, but especially with group 1. Silver is insoluble with almost everything except for nitrate. And I think chloride is usually soluble except with a few exceptions. This is just from memory of the rules, but there is a chart. I'm never expecting you to memorize anything. And so you doing a problem like this, predicting the products and then breaking down. I'm going to say, look at this. So what do? In a double displacement, we're going to swap places. Cu is 2 plus, so it'd be CuNO3 2. And then you would look up on the chart. What's the solubility rules? Well, nitrate is always soluble. Then you'd go, what about barium? Barium, sulfate, and you go, oh, is that soluble? And the answer is barium sulfate is not soluble, and so that's a solid. If you're breaking this down into the net ionic equation, the net equation is just barium 2 plus, just sulfate 2 minus goes to barium sulfate. And so this guy's going to have magnesium phosphate. Magnesium 2 plus, phosphate 3 minus goes to magnesium phosphate solid. But you have rules. There's rules to help you with this. Once again, another solubility interactive. So, and a net ionic equation. So once again, we just did this one. So just working it out, what's the net ionic equation? You're basically looking at what doesn't change. What is the driving force? barium 2 plus aqueous plus sulfate 2 minus aqueous goes to barium sulfate. Basically, you should have something like this. This is what I'm looking, whenever I ask for a net ionic equation, something like this, where barium is going and sulfate forms the solid. The nitrate and the sodium are just going to stay aqueous. And so because they're aqueous at the beginning, they'll be aqueous at the end. They cancel out when all is said and done. And you do the same thing there. Now, the only other thing to note is any acid-base net ionic equation, if they are strong acids and strong bases, the net ionic equation for acid base is just H positive plus OH negative goes to water. I just wanted to quickly go through that, just show you examples of what some of the problems for this chapter could look like. Now, here's the actual test. This one I gave a lot of problems because I wanted to be less likely chance, because one, there's a lot of material, and two, there's less likely chance for us, like each problem would be worth a little bit less. But here's what they had. So there's going to be Lewis structure stuff. There's going to be Vesper model stuff. There's going to be like reaction type stuff. Oxidation state, net ionic equation, sigma and pi, balance equation, name the type of equation, all sorts of various things. Net ionic equations, formal charges, like hybridization, which of these guys are polar and stuff. And so, but notice, this is, I gave them electronegativity. I also gave them, this is a different solubility chart, but it's still very similar. This solubility chart is the one from the Achieve homework. Slightly different, but basically everywhere it's clear, it is soluble. Everywhere it's shaded in was insoluble. I'm not cruel. I give you the solubility rules. You just have to know how to use them. Okay. So start drawing the Lewis structure for potassium chloride. Not potassium chloride, just chloride. 1 minus. So how do we go about doing that? Gotta remember. It needs to have all the electrons accounted for. All the outer atoms should have an octet whenever possible. So we have 7 from chlorine. We have 12 from the 2 oxygens plus 1 from the negative charge. So how many electrons do we have total? 20. So I'm going to start Cl. O. That uses up 4. Then we're going to put 6 on either. Oxygen. That uses 12. So how many do we have left? We have 4. So we're just going to put bam. Now, is that a valid Lewis structure? Sure. Is that the one with the lowest formal charges? No. We could draw one other structure. So right now, we drew this on, you would have formal charge of -1 there because we count 1, 2, 3, 4, 5, 6, 7. Oxygen has 6. 7. And this one has 1, 2, 3, 4, 5, 6. We should have 7 from the chlorine. So the formal charge adds up correct. So this is still a valid answer. Still a valid answer. If I just say draw a valid Lewis structure, that is acceptable. One other structure you could do, though, is drawing a double bond there. How does that change things? Well, chlorine now has an expanded octet, but formal charge of 0 there, formal charge of 0 there. So either of those would have been an acceptable answer for what I was asking for. Because I just say draw a valid Lewis structure. Number 2, what is the hybridization of bromine in BrF3? So we got some of these guys, you got to draw them. BrF3. Br has 7, F each has 7, so 21 from bromines, from fluorines, total of 28. So let's go back. We're going to be jumping back and forth between the dot cam as a reasonable amount. So dot cam. So 28. Put bromine in the center, fluorine, fluorine, fluorine. That's 6, so we're down to 22. We put 6 on every fluorine. That's done. That knocks it down to 4 left. 1, 2, 3, 4. 1, 2, and now to get hybridization, we have to count electron domains. We have to count electron domains. How many electron domains do we have on bromine? 1, 2, 3, 4, 5. So 5 electron domains means we have the ability to we need 5 hybrid orbitals. Now, when we use hybrid orbitals, we start with the S. That's 1. We use the P's. That's up to 4 now. And then we keep going to the D. Now, 1, 2, 3, 4, 5. So SP3D. Now, please note, when we go into lab next week, lab is not very hard. Lab is not very hard at all. You'll come in, you'll maybe get some basics, but you could do your lab right now. It's something you could do completely outside of lab. So this lab period might be a good time to take your test if you don't have any other time during the day, because you're supposed to have the 1 to 3 period free. But so the correct answer is D. I got to pull up the Word document. Now, which of the following reactions would occur according to this thing? So what we're saying is, which of these reactions is the solid higher up than the other thing? So you have to just compare this to this chart on the right here. So lead is down here. You look, magnesium is up there. Magnesium is higher than lead, so lead will not replace them. So no for the first one. Gold is way down there. It's kind of off the screen. Cobalt is right there. Gold would not replace it. Cadmium. Cadmium is right here. Copper is right there. So cadmium is higher than copper. Cadmium will replace it. And so check mark there. Aluminum is way up here. Silver is way down there. Aluminum will definitely replace silver. So we look here. We have aluminum, we have silver, gold's down below platinum. We have manganese, we have cobalt, we have cadmium. Oh, jeez. Scrolled too far. Oh, dang. But okay. What is the formal charge of these compounds present? So what is the formal charge? How do you do formal charges again? Formal charges is you count half of all electrons and bonds and all lone pairs. Half of all electrons and bonds and all the lone pairs, and you add them and compare them to the valence electrons. Remember, carbon is group 4, has 4 valence electrons. Nitrogen is 5, has 5. Oxygen, 6. Fluorine, chlorine, bromine, iodine, 7. So carbon should have 4. Looking at carbon, it has 2 from the hydrogen bonds and 2 from the double bond to nitrogen. So 4 valence electrons, 4 electrons provided. Formal charge of 0. The center nitrogen has 2 from the double bond to the left, 2 from the double bond to the right, a net, like a total electrons around it of 4. Once again, valence electrons of 5. It's lost one of its valence electrons, so the net effect is +1 on nitrogen middle. The nitrogen on the end has 2 from the double bond and 4 from the lone pairs. So it has 6, 1 more. So it has a net effect of -1. So the answer for 4 is simply 0, +1, -1. You'll note the net charge cancels out because this is a neutral molecule. The last one on this page. What is the molecular geometry of radon tetrachloride? Remember, we start with electronic and then we work our way to molecular. So going to the doc cam, we have to pull out and draw this guy. You don't have to be pretty, but you have to draw. Rn, radon has 8. Chlorides each have 7, so 7 times 4 is 28. 28 plus 8 is 36. Okay. Redraw this. Rn. We'll put Cl, 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 Cl. That uses up 8. Down to 28. Then we have to use 6 on each chlorine. That's 12. That's 18. That's 24. I'm just remembering that 1 bond, we need 6 more electrons to make it 8. So I'm just going fast right here, but I'm just going 2 plus 6 is 8. That leaves 4 electrons left. So what do I have to put? I put them on the radon. 1, 2, 3, 4. So to get the electron domain, we look at the electron geometry, we look at the number of electron domains. What do we have? 1, 2, 3, 4, 5, 6. The electronic geometry is octahedral. However, we look at the number of bonds versus lone pairs when we go for the molecular geometry. So just looking at from the molecular standpoint, this guy would be square planar because it's 1, 2, 3, 4, and 2 lone pairs. If that is hard, if that is unclear, doing the lab will give you lots of practice with this. Doing the lab will give you lots of practice with this. So work on that lab with the Lewis structure lab. Square planar. That's lab number what? 4. So that's answer B. What is the oxidation state in manganese and MnO4? I was thinking that was supposed to be MnO4 1 minus, but based on the fact I don't see a negative sign, we'll just go MnO4. So it's all context. Oxygen is almost always -2. So in this case, -2 times 4 is -8. So in order to make this neutral, that has to be +8 on manganese. Once again, I'm pretty sure it's supposed to be 1 minus, but I don't see a 1 minus, so either it got deleted or it got shrunk or whatever. The answer should have been what, +7 if that was 1 minus, but without a 1 minus, I have to accept 8 is the correct answer. So now this one, sodium carbonate plus barium sulfate. What is the net ionic reaction? Now, this case, in some of the cases, they say barium sulfate was a solid. In some cases, barium sulfate is mildly aqueous. Jeez. But okay. If you broke this down, if we go with the, oh, this is going to react, what we want to do is we want to go and check the chart. Let's first check the chart, and then we'll go from there. Barium sulfate and sodium carbonate. Oh, where's the dang thing? Going all the way down. So we have right here barium. That may have been a goof on my part. Barium sulfate says it's supposed to be insoluble. Barium carbonate also insoluble. Depending on which chart you look at, you might have this being insoluble or soluble. Obviously, this test has a bunch of goofs. Any of sodium is pretty much always soluble. So, going back up. Going with what I was attempting to do. I'll show you what I was attempting to do, and I'll show you another possible answer based on the two things. Based on the fact of what it should have been and what it was. So you would have split this in part into 2 sodiums and 1 carbonate. And what I was trying for was barium 2 plus and sulfate 2 minus. But then again, that makes the assumption that this is soluble. This is soluble, and that isn't necessarily that soluble. So you would have split up and to say, oh, then we'd have barium carbonate on the other side, and then you'd have sodium, 2 sodiums and 1 sulfate. Now, what would happen when you do a net ionic equation is, if 2 sodiums are there, 2 sodiums cross off there. But then again, if I was going for leaving this as a solid, you could have had something like this. That when you mix this guy together, you could also have had something like this, where barium carbonate. I don't think I was trying to be this tricky. So I'm thinking I just screwed something up. You could have possibly also had something like that, where the barium swaps out with the carbonate. But either way, the sodium acts as a spectator ion. Not all tests are perfect. We'll work with that, and the errors that get made usually work out for your favor. Okay, this one, sigma and pi bonds. This one's actually relatively straightforward. Shouldn't be any errors here. What is a sigma bond? A sigma bond is any type of single bond. All atoms have them. The pi bonds are the double and triple bonds, the bonds in addition to the single bonds. So count all the bonds one time for your sigma bond. So I'd say one, let's get my mouse over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 sigma bonds. Then for pi bonds, you count the double bonds. If you had a triple bond, that would be 2 pi bonds and a sigma. So right now we only have doubles, so 1, 2, and 3. Draw a Lewis structure for S2. That's just going to be straightforward. I mean, I'm not even going to. I'm not going to ask you for 10 real quick because 10 is just a combustion one. It's a balancing equation. What you should have had is CO2 and water as a product, and then you would have to balance that thing. But I'm not going to. I don't have anything like that on the test. Jumping straight to 11. So classify the following as either combination, decomposition, single displacement, or double displacement. Also known as single replacement and double replacement. So single combination is 2 things go into 1 unit. So iron Fe3O4 plus oxygen goes to Fe2O3. Even though 4 magnetites and 1 oxygen forms 6 hematites, is combination. 2 different units come together to form 1 type of compound. Cadmium nitrate plus magnesium sulfate forms magnesium nitrate and cadmium sulfate. The cadmium and magnesium switch places. That's a double displacement. Sodium plus water forms sodium hydroxide and hydrogen gas. You may not look it, but H2O is really HOH. So what are you switching? You're switching one of the H's with one of the NAs. So you're forming, instead of HOH, NaOH, and the H is leaving. And so in that way, you're forming, this is a single replacement. You're replacing H with a sodium. And this one, benzoic acid, well, phenol plus lithium hydroxide forms lithium phenolate, or phenolate, yeah, and water. This is just, once again, a double displacement. We're swapping an H with a Li. In this case, there's no decomposition. Let's keep going for a little bit more. Okay. What is a polar version of the compound SF4Cl2? One of the tricks here, polarity is all about canceling out, is things not being canceled out. Whenever you could draw a compound, there's multiple different ways to draw it. Typically on tests in the past, I've asked questions such as draw a polar and a non-polar version. And typically most people will swap them. So this time around, I just asked for 1 because F4Cl2, there's 6 atoms coming off of here. You do the Lewis structure, you would get S is an octahedral compound that looks like this. And so we have to put these atoms around here in a particular pattern. To cancel out, you need equal and opposite pairs. So if I call this A, this is canceled out by A prime. B is canceled out by B prime. C is canceled out by C prime. So if I wanted a nonpolar compound, you would have to have C and C prime to match, A and A prime to match, B and B prime to match. And as long as there are an even number of each atom, you could do that. But because we asked for a polar compound, we want one of these not to match. So the easiest way is put a Cl here and a Cl any other spot that isn't A prime. Any non-A prime, we put the rest of them around it. Done. Because A prime and A are not the same. They don't cancel out. C prime and C are not the same. They don't cancel out. So this guy is polar. B and B prime cancel out, but as long as not everything cancels out, we are polar. So the only way to make a nonpolar compound is matching the primes. So I'll do like maybe 2 more, and then we'll have to finish this up on Monday. What is the electron geometry of the compound SO4? SO4, 2-. And then finally, what is the net ionic reaction of HClO4 and CSOH? So we'll do those 2 real quick, and then we'll get... So what is the electron geometry of SO4, 2-? So 6 plus 6 times 4 is 24 plus 2. So we have 32 electrons. Putting this here, O, 4 O's, that uses 8. We are down to 24. Putting 6 on each, that is another 24. Now, because this is electron geometry and not a Lewis structure, we are done. We don't have to keep going, but we will keep going just for the sake of showing you something neat. So if you look here, how many electron domains are on sulfur? 1, 2, 3, 4. So what is the electron geometry? For 4, this is tetrahedral. Now, is this the best structure for this? No, because this has 4 formal charges on oxygens and a positive 2 formal charge on sulfur. So how can we manage that, get that array? You would take a double bond. You'd take a lone pair, turn it into a double bond. You'd take another lone pair and turn it into a double bond. So now we've removed 2 of the formal charges and given sulfur an expanded octet. Now, why is that not important? Because a double bond and a single bond count as 1 electron domain. They do not differ. So how many electron domains do we have on here? 1, 2, 3, 4. So regardless of which way I drew it, the answer is still tetrahedral, because there's still 4 electron domains. Now the last one that I'll do today, HClO4 plus CSOH. What's going to happen? Double displacement. You're going to have HOH, which is H2O, which is a liquid, and you have CSClO4, which if you look on the table is aqueous. So breaking this apart, H plus, ClO4. That's a strong acid. That's a strong acid. Cesium hydroxide. That is a strong base. Goes to H2O liquid and CS plus aqueous, ClO4 minus aqueous. And we go H plus water, not the same. ClO4 is the same. CS, the same. OH minus, water, not the same. The net ionic equation is just H plus aqueous, OH minus aqueous, goes to water, liquid. And this is true for every strong acid, strong base. The net ionic is just H plus and OH minus goes to water. So that's where we're going to stop. Out of time. We'll pick this up on Monday, finish the tests, maybe start on the next chapter. But so answer that survey. Tell me when you can do that test. Maybe we'll plan on some people taking it like Tuesday during the lab period, but whatever. You're going to get that done next week. The way I will talk to you again a little bit later.